All right, so let's talk about a little bit about relational algebra. So a lot of what we take for granted today, computers and programming languages and databases, at some point never existed. But even before they ever existed, folks were already thinking about it. Right? We're already creating all the conceptual model around these data stores, right? If we had a data storage, how would we interact with it? Okay, people were already thinking about a conceptual model of what these things might look like, right? And a lot of effort was made to create all the mathematical foundation behind data storage and whatnot, right? So out of that effort, we have relational algebra. Relational algebra is a set of operations and transformations that take into account set theory. Right? You have basically that's what a database is. Right? You have just a big bag of data that you want to be able to operate on another big bag of data. Right? You have these different tables being different buckets of data, right? That somehow are related to other elements in another bucket of data. Right? And somehow you want to join them, or you want to operate on subsets of those. Yes. So relational algebra is taking a look at a lot of these operations that you would expect. Right. You need to be able to retrieve things. Right. You need to typically you want to retrieve them based on some criteria. Right. You want to pass some kind of predicate. Only the ones that meet a particular criteria I want to see. I don't want to see the entire data set. Right. And also, those data sets probably will have all sorts of attributes and properties, right? Maybe I don't want all the properties. Each one of these data points might have several dozen of attributes. Maybe I don't want all of them. Maybe I only want 2 or 3. So these operations are looking to how do you navigate these huge data sets, right? Out of the millions of records, how can I select just a few dozen, and once I have those data sets, how can I only filter only the fields that I care about, right? So if we imagine the data set being one long row, set of rows of records, how do I filter vertically, right? Which rows do I want, and then how do I filter horizontally? Which fields do I need out of those? Right? So basically, how do I pinpoint, right? What is it that I'm looking for? So between the first two, select and project, allows us to filter in both dimensions, right? Being able to again filter out only the records that we want, and then filter out which subset of the fields do we want, right? So select and project. Sort is mostly for just human consumption. Humans, we insist on sorting the world, that we want to see the world sorted in a particular way. Databases don't really care about sorting, but for our purposes, we like things to be ordered in a particular order. So sort allows you to do that. So all these other ones, sort and rename and extend, all these are operations or transformations on data that we've already identified, right? And we want to modify it somewhat. Maybe the field, we might want to change the field names to be something else other than the original field name. And oftentimes this comes handy if you have 2 different buckets of data sets, right? And some of the data sets on one of them. One of the buckets have exactly the same attributes as maybe another data set, right? In a different bucket, and you have attributes or properties that have exactly the same name, right? If you bring them together and you join them somehow, right? There won't be any way for you to distinguish which one is which one belongs to which bucket, right? So rename allows us to deal with those kinds of issues. Other things that you might want to do is that as you are extracting this data, and somehow you're combining it, you might want to, on the fly, calculate other things, right? So that based on each one of the records, maybe you can generate a virtual additional attribute that is a combination of the other attributes, right? You can you have the first name, the last name, the middle name. Maybe you want to on the fly you want to calculate what the full name might be, right? So the full name might be the concatenation of 3 other fields, yes, or it might be the summation of other fields or the multiplication of other fields, right? Of each one of the records. So extend allows you to add new fields to the original data set. GroupBy allows you to, in the resulting data set, there might be some data sets that might have values that are the same across the data set, right? Maybe you retrieve all the students in a particular class or a particular section, and you might want to find out well which ones are sophomore, which one are seniors, right? You want to group them together because you want to treat one particular set of folks in a different way, right? And so GroupBy allows you to do that. It allows you to identify which records fall in the same group. So these are operations that allow you to operate on an individual data set, right? But oftentimes you want to operate on multiple ones, right? Or you want to combine multiple data sets. So for instance, these are operations that deal with binary, operating on two data sets, right? On 2 tables. So product, join, semi-join, anti-join, right? These are all take two tables as a parameter, and then somehow relates them somehow. Okay. So for instance, it might be that I like to be able to consider all the data sets on one bucket, with all the data sets in another bucket, right? And there might be a little bit. Now, some of the combinations might make no sense. Might make no sense, right? Where that might have no relationship whatsoever, right? Ideally, you want to identify which data sets make sense to join or to relate. For instance, if I have a huge bucket of addresses and I have a huge bucket of people, it might be that 2 or 3 addresses belong to one person and 2 other 3 addresses belong to another person, right? But I don't know what they are. I need to consider all the possibilities. So, for instance, for one person, I don't know which ones are the addresses that belong to that one person. For that one person, I need to start looking at the other set of addresses until I find those addresses that actually belong to this one person, until I find them. And the other way to do that is to consider all possibilities, right? Just to do a full scan of that data set until I find those 2 or 3 out of the hundreds of addresses, which one belongs to this one person. Yes? And then when I go to the next person, I need to do the same thing again. I need to scan again the list of addresses until I find all those 2 or 3 sets of addresses that belong to this one person. Does that make sense? Okay. So I need to consider all possibility combinations. A lot of them I'll just throw away because they make no sense, right? I might have something like this. What the heck did I do? Right. Oh. Right. That here I have people and I have maybe addresses. And some of these addresses belong to this one person, right? So they might all have references to that one person, saying I'm the address of that one person. And here I have another. These 2 addresses belong to this other person, right? And so usually I want to group them together somehow, right? But the only way to know and find out which address belong to who is to consider all the possibilities, right? That I start with person 1. I go through each one of the addresses and say, well, this one yes, this one no, this one yes, this one no, and this one yes. But I've gone through all the possibilities. I need to consider all the possibilities. There's no way for me to magically know which ones are the ones that match that one person. I have to scan all the possible addresses. Yes, okay. And same thing when I go to the next person, I have to do the same thing again, right? This one no, this one yes, this one no, this one yes, and this one no. But I still have to consider all possibilities. Yes, right? And that's what a product does. A product takes all the elements of one of the data sets and takes all the elements of all the data sets and lists for us all possible combinations. Okay? Lists all possible combinations. Some of them might make no sense. Like if I want to combine this person with that address, it makes no sense. Yes? But nevertheless, I had to visit it to realize that it made no sense. Right? It says, oh, no, this one doesn't match my person. But I had to calculate it anyway. Right, so what product does allows me to returns all possible combinations that I need to consider. Yes?
When you talk about making sense of matching different records
Yes.
from different tables, do you mean, are you...
That somehow these will have a reference back to the person saying, hey, I'm that person's address
key.
with a foreign key.
So
yes.
it takes like whatever n times n times.
Exactly.
To
yes.
figure that out.
So exactly, it would take me the size of this times the size of that time to figure that out anyway, because I have to visit it.
Yeah.
It's time that I have to spend to realize that it makes no sense, but it's time that I spent anyway to decide that. Yes. Then we have then we want to operate on that product, right? It says, okay, now that I have all possible combinations, which ones make sense and which ones don't, right? Which ones have actual relationships between one of the data sets that belong to other elements in another data set, right? I need to identify which ones are actually related to one another, and that's such a common operation that basically it's a combination of a select and a join. Right, I want to look at the product, and then I only want the subset where one of the foreign keys matches the primary key of the other. So it's a select on a product, right? Right. So and that's such a common use case, right? That we are filtering. I don't want all the combinations. I only want the subset of combinations that make sense. It's such a common operation that we give it its own name. We call it join, the join, right? Which is first to do the product, and now do a select on that product, right? Well, that's the mathematical definition. We don't actually do that. There's all sorts of optimizations that we try to avoid to have to do that, because this is, that product is very, very expensive, right? So anything we could do to avoid to actually doing the product, we'll do. But nevertheless, it is the mathematical underpinning, right? Now, some of these, oftentimes, we might be interested not only on the ones that match, but oftentimes we might be interested on the ones that didn't match as well. Meaning, I want to identify as the one that matched, certainly, but also give me the ones that didn't match, because I want that information as well. Okay, so that's we'll talk about semi-joins, right, where we match some of the records, right. Then we have anti-joins where we want to know like the inverse, right? It says, well, which ones did not match, right? Which ones did? So basically, this is like set theory, right? You have different sets that you can either intersect, right? Unions are the capability of being able to just just concatenate one after another. And the ones that didn't match as well, we might want as the outer join. All right, so let's look at the first one, select. Right. So select is has its own formal mathematical representation. Again, this is before databases were even invented. Right. We were already thinking of, well, if they existed, how would we interact with them? So basically, the formal definition is that it takes as argument first a single table, like a student table, and then it takes a predicate. Right? So I want to filter. I want to identify those records that meet that criteria. Right? And the ones that meet that criteria, that's the one I want. Right? So out of the thousands of records, only return to me, the dozen or so that match that criteria. Okay? So here's an example where you have the student table and the criteria, the graduation year is 2004, of which I will only have, out of the 46,000 students, maybe only 2,000 match that criteria. So here's that criteria could be combined, could be a Boolean expression where you might have a more complex predicate with ands and ors and whatnot. and you know, you could represent it in algebra, relational algebra as well. So here's a couple more. Notice that we are assigning the results of each one of these, right? We're assigning it to a symbol, right? We're assigning it to a variable. Right? For instance, Q3. Presumably, this returns a subset of the original table. So the original table might have been student, right? This returns a subset of a table, which can be used itself as another table, as an input into another selector. See that? Right, so operations can be nested, right, where the output of the inner select gives back of something that looks like a table that can be used as an input to another outer select. Okay? So here we have an inner select with its own predicate, with its own student, and then you have an outer select, right? We have its own predicate, and the input table is the output of the inner select. Okay. So this nomenclature of assigning a variable allows us to write it a little bit easier to read, right? Where the result of selecting is assigned to Q1, but then Q1 is used as an input for the next one. Yes? And we'll see later that this is basically views, right? That we can name our queries so that we can reuse them as input to other ones, right? And we'll talk about that a little later. You can also represent it graphically, right? Where you have the input students, which we then apply a predicate that generates the result, and then it gets filtered as we navigate backwards, starting from the student, and we navigate up the tree to an ultimate result. Okay. So that's a graphical representation of that query. Project is if select filters vertically, right, identifying all the different rows that match, then project kind of filters horizontally, right? Which fields, right, of those records do we want? Right? It might be a couple dozen, and we might only identify the ones we care about. So it takes as input either a table or maybe a result of some query, right? It takes that as an input, and then you list the various items, fields that you want. You will see in like MongoDB and many other databases, you'll see these operators, right? Literally called project, right? That you can list, as an argument. You can list which fields you actually want. You might not want all of them. By default, it returns all the fields, but here you can list only the ones that you care about. Right? Oftentimes, these two are taken together, right? Where the output of a select statement is then used as an input into a project. Right? Very common. That's what the select statement is, right? The select statement has, you list the tables in the from clause, right? You do in the select clause, you list the fields that you want, right? In the where clause, you specify the predicates, right? So basically, it's a combination of these two, right? Of selecting and then projecting. And again, we have the graphical representation of this operation. Now, some of these queries might be meaningless, where the output of an inner query doesn't actually produce anything that can be actionable with the outer query, right? Where the output of the inner query actually comes back as an empty table, right? Or it provides output that the outer one cannot operate on. Okay? So, for instance, here we're selecting the student and only the student name, right? So, meaning we have one single column of records that I cannot select because my predicate is expecting a major ID, and there are no major IDs that you can provide me in the inner query. See that? Right, so there's no way for me to operate in the major ID because I don't have that column in the resulting query, inner query. So this is a meaningless query, right? Sorting, as you might expect, right? It takes certain fields as an input and then sorts by the first field and then by the second field, right? And takes as an input a table or a set of records. Either this could be a projection, it could be a select statement, right? That generates that query and not necessarily a static table. And it's only meant for display purposes, right? For human consumption, right? Other than that, it has no meaning. Rename allows you to rename a field. So, for instance, instead of rename the field student name to maybe CS majors. Now, oftentimes this is very useful if, for instance, if a table is joining with itself, right? If you have a join where you have a table that has a foreign key that points to a primary key of some record in the same table, basically what you'll end up is with duplicate fields, right? Fields that have the same name in from because it'll treat it as if it were two tables, right? It'll grab fields from one of the tables and grab fields from the other table. It'll combine them, but this happens to be the same table, right? And since it's the same table, you end up with duplicate fields. So what rename allows you to do is rename them, right? So that they have a meaning for you. Extend allows you to calculate new fields on the fly, right? So that you can generate a brand new field name, like over here we're identifying whether it's a graduating class, and we're computing the graduating class by subtracting from the graduating year. We're subtracting from the year that the college was established, right? So that would tell me, you do the first, second, third, fourth graduating class. GroupBy allows you, like the name suggests, takes a table as an argument, and then allows you to group by whatever fields you give it, right? So that if the records have the same values for those fields, they would fall in the same group, right? In the same category, right? And then you can operate on the group, right? And you can aggregate things, because if you have, out of 1,000 records, you might have a couple hundreds records fall in one category and a couple hundred fall in another category, and so on and so forth. Well, the original records are lost. You don't have access to the original record. You can have access to aggregate operations on those records, right? Like, for instance, if you have a field in there where you have the value of a quiz or the number of courses and whatnot, you can aggregate those values, right? You can add them up, you can average them out, you can do the max and min, things that you can aggregate those values and then come up with a single value. So here you can provide a list of aggregate functions that you want to operate on the resulting aggregation. So here's an example where we are taking the student table and we're taking we're grouping by major ID. Right? That means that all the students that fall in the same major are in the same group. Right? So if we had, I don't know, what do we have, 9 students, or in our example, you might have 3 that fall in CS, 3 that fall in math, and 3 that fall in drama. Right? So you have 3 groups, right? And they all have, those students might have in the original records, they might have a graduating year, right? And maybe we want to calculate for each one of those groups, right? In the CS, in the major, in the math, and the art, and the drama. We like to calculate the range of when folks are graduating, right? So we could calculate what the minimum and the maximum graduating year is, right, for that one group. But the original graduating years, right, and the original student names and the original major IDs, those are lost, right? You don't have access to them to operate on them. You can only aggregate them somehow, right? So here's an example of having just some random list of students and looking at the major IDs. So 10. So we have 3 in major ID 10, 4 then in 20, and 3 then in major 30. So if we group by major ID, we see that Joe, Lee, and Max fall into 10. Amy, Sue, Kim in another group, and whatnot. And here we're looking for, I guess, the minimum. Yes, we're looking for the minimum, right? So we identify the minimum 2004, 2001, 2003. So these are going to be squished into just one single value, of which we only keep the fact that we have a 2004, right, the minimum, or the maximum here, 2005 and whatnot. Okay. Right. So it results into these three results, right? So we lose the original graduation years, we lose the original courses and majors and whatnot. We do keep the value by which we were grouping, that we have, right? Because they all have the same value, right? We do keep any of the aggregate values, minimum and max, right? Those we keep, but the individual ones are lost to us. We don't have, and that's very important later on. When we look at the limitations of GroupBy, we'll talk about some of the limitations, how to get around that, right, by using maybe things like halving and whatnot. All right, so now if you provide multiple grouping fields, like a combination of majors and graduating year, then only the records that have both the same major ID and the same graduating year, those fall in the same category. If you don't have both the same, they don't belong to the same group. So if you look at the original data set, we have, let's see, which ones are the same? We have major ID, 10. Anyone else with 2004? No. How about 20? No, I guess we don't have any. Right? Oh, actually, no. Oh, no, I guess we had two. Right? We had two that were in 2001. We had two that were in 2004. Is that correct? Apparently we do. 2020. Okay, yeah, we had these two that were in 2001, right? And I guess we had two in 2004 for major ID 10, right? So notice that that these are the groups and tells us how many. Notice that there are several. There are many types of aggregation functions. One of them is count. Count tells me how many are in that group. And ideally, we ask the count on something we know it's not going to be null. Right? Count the IDs, and then we know these are primary keys. We know they're not going to be null, right? So we count how many primary keys there are. So it comes up to 2, 1, 2, and 1, 1, 1, 1. Right, so there's two of those, one of those, and two of those. Multiple grouping fields, and oh, okay, here it is. Grouping whole tables. If you group the whole table, meaning you don't provide, if you don't provide a grouping field, right? What GroupBy interprets that as the entire table being one single group. I mean, they all belong to the same group. They're all in the same group, and then you can operate on the entire data set, on the entire table. So here we are applying the aggregation min on the graduation year, so that we can know, who's the latest, who's the last one to graduate, right? Or earliest one. Earliest? Yeah. If you don't provide just list distinct grouping fields. Wait, if no aggregate function are provided, then result just list distinct grouping fields. Okay, I don't have an example for that. So here we have. Right, so we have oh, okay, so yeah, so we have several aggregate functions that some of them consider the if the same value gets counted the same time, right? We would like to know if it's repeating or not, right? And sometimes we want to count it as different, only when it's unique. And for instance, for count, we might want to know if they're distinct or not. Obviously, if you're using our primary key, then obviously they are going to be unique, right? But you can count on something else that's not unique, maybe you want to count on emails, right? And there might be several emails that are repeated over and over in multiple records in a table. So you can decide to count distinct, meaning make sure that this particular field does not repeat, right? Obviously, count distinct is much more expensive than just plain old count. The count distinct would have to keep track on whether it has seen a particular field already. It's a value. It has to keep track of it. This is a value. And for every value, it has to make sure that it's not already a value that it's seen. So it's very, very expensive. Notice that here we're counting major IDs. And major IDs, in the student table at least, it's not unique. In the department table, it is unique, right? But in the student table, it is not unique, right? So here we can count how many distinct majors there are. So it gives us this 3 majors. Right, whereas over here, right, we count the entire number of students. So this gives me the entire number of students that there are. Now notice over here, if we would have allowed folks not to enroll or not to declare themselves in a major, some of these major IDs are going to be null. Yeah. So some of this count, you got to be careful. It might be less than what you would expect. Right? Because you would say, well, no, how can there be? There's 36,000 students. Why is it coming back as 26,000? He says, oh, because there's 10,000 students who are undecided. Right? They have not established so that might be null. So if you're expecting to count something that is not null, you want to stick to the primary key, not a non-primary key like we did here. Okay? In this particular case, we do want to do this, right? Counting how many majors there are in distinct. Right, not null. So careful when you are counting fields that might be null. Right? That might be less than you would expect. All right, let's see. All right, so let's take a look at an example where we might want to ask certain things like maybe what are the most A grades in any section, right? Where we might have the following data. We might have 18, right? Where we query and say, okay, well, we query the enrollment table. The enrollment table, remember, it says which student was in which section and what grade did they get in that particular section. So we're looking for only those enrollments for which we got an A. Notice we have 1A in section 13 with 2 A's. In section 53, that must be my section, and then we're feeding that query 18. We are grouping it by section ID, right? So let's see. So basically, this 53 is going to end up being one group, and this is going to be one group. And we're going to count how many of these do we have. So we have 2 for this and 1 for those, right? So that's what we get here, right? We have that. Section 53, we have 2, and section 13, we have 1. And then we can take the entire table here, right? Notice that we are not providing a grouping field, right? So it's taking it as the whole table as one single data set, and out of that table we're counting what is the maximum number of A's, right? So out of these 2 is the biggest one, so it comes out to be just 2. Right? Okay, so we identified what are the most A's across all the sections, right? And in the quiz, you'll get something like this, right? You'll be given a couple of pieces of data, right? And then you'll group and calculate something from that grouping. Now graphically, you could represent this way, right? You have the enrollment, you have to select the A that feeds into the GroupBy, that feeds into the outer GroupBy, right? Come back with the value. Now another question. The other question might be, okay, now that you know what are the max number of A's, what if the original question might have been, which section had the most A's? Right. So that's a little harder, right? Because by the time you get here. By the time you get here, notice that you don't have the section anymore. It's lost. It's lost to you, right? It was here, but it's not here. Right? When you group by, that's one of the limitations of group by, right? That once you do the grouping, you don't have access to the original record that you group by, right? So that 53, that 13 is gone. So there's no way to say, okay, well, now that I know it's 2, which section was it? Oh, it's gone. I don't have it anymore. Right? We could hack through this a little bit by joining these two. Right? We can join this with that and say, okay, well, give me the section where 2 is equal to 2, right? And it gives me the 53. Right? But what if you have two sections that have the same amount, right? There would be any way for me to tell which one, right? Anyway, so let's see. Let's continue to look at product, and we'll do that next. This is getting too long.